Okay, so remember that we started to talk about conditional probability, and so we defined, we are using the notation P of A given B. So A slash A with a vertical line segment B, that I'm going to read that as A given B. So this is the probability of A given B, but more appropriately it is the probability of A, probability that A occurs given that B occurs. So basically, whatever the underlying experiment is, if you carry that out, you are given the information that B has occurred, which means that the outcome is in B. So given that information that the outcome is in B, then what's the probability that the outcome is also in A, right? So, well, if you think about it, if we are asking what's the probability that the outcome is in A, given that it is in B, well, that's the same as asking then what's the probability of A intersect B relative to the sample space B. Okay, so when you are, so in the conditional probability here, I'm going to refer to B as a condition. So it's the probability of A conditioned on B. Okay, and so last time we did an example where we saw that the probability of A given B is larger than the probability of A. Today we want to do another example. Let's roll 2 dice. And then we know that there are 36 possible outcomes. So if I roll 2 dice, there are 36 possible outcomes, so which are given in this table. And you guys have this table in your notes from before. So here I'm going to define a couple of events here. Let A be the event that is sum of 7 occurs. B be the event that is that exactly 1/6 occurs, and C be the event that a 4 and a 3 occurs. Okay. You roll 2 dice. A is the event that is sum of 7 occurs. B is the event that exactly 1/6 occurs. C is the event that a 4 and a 3 occurs. Could somebody please tell me what's the probability of A? Now, what is the event A, by the way? In my table, notice that I highlighted some of the some outcomes within a green. Well, I bounded some of the outcomes within a green curve. I bounded some of the outcomes within a red curve, and I bounded some of the outcomes within blue curves, right? So which one is A, which one is B, and which one is C? So A is green. A is green, okay. Which one's red? Red is C. And which one is blue? Right? Okay, so what's the probability of A then? What's the probability of A? Well, that's the number of elements of A divided by the number of elements of the sample space. And how many elements do I have in A? You said how many elements does A have? 6. So this is 6 divided by 36, which is 1/6. Okay, so what's the probability of A conditioned on B? What's the probability of A given B? Well, it's the probability of A intersect B, probability of A intersect B relative to the reduced sample space B, right? Since you know you're given that B occurred, right? You are given that B occurred, so that reduces the possible outcomes to the elements of B, right? Am I making sense? So what's the probability of A intersect B relative to B? Well, it is the number of elements in A intersect B divided by the number of elements of B. Well, why does it work? Because remember, the outcomes are equally likely, right? So I can just divide the number of elements of A intersect B by the number of elements of B, and then what is that equal to? A intersect B has how many elements? A intersect B, B is the blue, A is the green, right? So there are exactly 2 outcomes there. And how many elements are in B? How many elements are in B? How many elements are in B? 10. So what we get is 1/5. Okay? So in this case, notice, observe again. Observe that the probability of A given B is larger than the probability of A. Right? Okay, so someone tell me what's the, I'm not going to do it, but let me ask you, what's the probability of A given C? And just give me the final answer. What's the probability of A given C? What's the probability of A given C? It's 1, yeah. So the number of elements in this is the number of, once again, number of elements in A intersect C divided by number of elements of C, which is 2 divided by 2, which is 1. So just to recap, if you are, so when we say find the probability of A given B, we are asking find the probability of A given that, find the probability that A occurs given that B occurs. Well, A occurs, B occurs means what? The outcome is in B, right? So you carry out the experiment, whatever the experiment is, whatever the outcome you get, that's in B, right? That's what we, when we say B occurs, right, it means that an outcome of B has occurred, right? So if we are given that B occurred, then the possible outcomes are restricted to the elements of B. So when you are given this extra information that B has occurred, you have to update your sample space. Now your new sample space should be B. And now, given that, what's the probability of A? Well, if you think about it, it should be the probability of A intersect B relative to the sample space B. Okay? So I want to rewrite the conditional probability of A given B. I want to rewrite. Remember, in the two examples that we did so far, the outcomes were equally likely, but there are problems where the outcomes are not equally likely, right? So in that case, I can't just divide the number of elements of A intersect B by the number of elements of B, because maybe the sample space is infinite, maybe the outcomes are not equally likely. So I want to find a little bit of a general formula for the probability of A given B. So let S be a finite sample space with equally likely outcomes. Let A be an event, so it is a subset of S. B be also an event, so they are subsets of the sample space. So in the previous two examples, we said that the probability of A given B is equal to the number of elements of A intersect B divided by the number of elements of B. This is what we said. What I'm going to do now is a bit of an algebra. In the numerator, I'm going to divide the numerator by the number of elements of the sample space. So A intersect B divided by the order of the sample space. Well, if I divide the numerator by the order of the sample space, I also have to divide the denominator by the order of the sample space, right? Is that algebra valid? Okay, now, can someone tell me what's the numerator? What is the numerator? Numerator is the number of elements of A intersect B divided by the number of elements of the sample space, right? So that's the unconditional, or the overall probability of what? The numerator is simply the probability of A intersect B, right? Relative to the sample space, right? And then the denominator is simply the probability of B, right? Because you're dividing the number of elements of B by the number of elements of S. So then we see that the probability of A given B is the probability of A intersect B divided by the probability of B. Okay? Now, notice previously we took the definition of the probability of A given B by what? So previously we took the probability of A given B, this, right? We took that to be the formula for the probability of A given B, right? And now we see that that's the same as this one here, right? But the first formula that I gave you for P of A given B only worked for equally likely sample space, right? If the sample space is finite, consisting of equally likely outcomes. Now, we obtained this new formula, right? But if you think about it, it's not talking about number of elements of, it's not dividing the number of elements of A intersect B by the number of elements of B. It's the probability of A intersect B divided by the probability of B. So I can take this to be the definition of, or I should say, it's appropriate to take this equation to be the general definition of P of A given B, even when the sample space may not be finite, even when you may not have equally likely sample space. So what I want to do now is make it a definition. So this is the probability. If you are given two events A and B, the probability of A given B is the probability of A intersect B divided by the probability of B, provided that the probability of B is positive. Obviously, if the probability of B is 0, right, then this conditional probability is undefined. If the probability of B is 0, then P of A given B is undefined. Now, if you have a finite sample space, the probability of B is 0 when? When is the probability of B 0 if you have a finite sample space? Well, I mean, all the events are in the sample space. When B is the empty set, right? When B is the empty event, right? In that case. However, if you have an infinite sample, if you have a sample space with infinitely many outcomes, for example, let's say your sample space is the entire real number line. Okay. Well, in that case, if the probability of an event is 0, it's not necessary that B is empty. Okay, we'll think about that later. But if you have your sample space like the real number line, then if the probability of an event is 0, doesn't mean that the event is empty. What it means, though, kind of like think about it as, in that case, B is kind of like a discrete set. Is that making sense? Okay, so we will get to that point later. So couple of remarks that I want to make here. It would be the following: the probability of A given B usually isn't the same as the probability of B given A. If the probability of B is 0, then the probability of A given B is undefined. 3, the probability of A given B complement is not 1 minus the probability of A given B. So that's just a warning that sometimes when you see the probability of A given B complement, you think about using the what's the probability of A complement? That's 1 minus the probability of A. So sometimes you tend to use that here, but it doesn't work. So number 4, the probability of A given B may be larger than the probability of A, may be smaller than, may be equal. Okay. So there are some examples. You will see that in the 2 examples that we did in the class, in both examples, the probability of A given B was bigger than the probability of A, right? But it could be that the probability of A given B is in fact smaller than the probability of A. And the probability of A given B may also be equal to the probability of A. Is everybody okay with that? Even though number 3 doesn't hold, right? The number 3 says P of A given B complement isn't the same as 1 minus the probability of A given B. However, you could say the following. 2 more things you could say. This is a complement like this. I can write a C to denote a complement, but I have been using a bar mostly. So probability of A complement given B, however, is the same as 1 minus the probability of A given B. Okay. So please compare this number 2 with number 3. Okay, this number 3 and this number 2. Okay. And also the probability of the union of AI, where I varies over some set, given the condition B, is the same as the sum of the probability of AI given B, where the sum goes over values of I in some set. But this equation holds for mutually exclusive events A1, A2, ... So when I'm writing ... I don't necessarily mean that I have I have a countably infinite number of events. It could be a countably infinite number of events, or it could be a finite sequence of events. It could be an infinite sequence of events or a finite sequence of events. Okay? Either way, it works. Is everybody clear?